Hello and welcome to the Daily Space for today, Tuesday, October 13th, 2020. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. There are certain words that are just pleasing. There are a combination of sounds and mouth movements that just feel good. Arugula. I, for one, am fond of the word arugula. Now, I'm not fond of eating arugula, but there's something pleasing about the word arugula. At the same time, science also has pleasing words. Another pleasing word is spaghettification. As its syllables are bounced back and forth along the speech palette, the word describes the end of stars, planets, asteroids, and maybe even people. This word, spaghettification, describes how the difference in the pull of gravity between the near and far side of an object can cause that object to be torn apart, tidally disrupted if you want the scientific term, and then those disrupted pieces can get strung out as they fall into the disrupting body, breaking up further as each piece is stretched and pulled apart, until all that is left is a long tail of debris spiraling in towards its doom. Now, if you're into cosmic death, spaghettification is a fascinating way to go. The human body, stretched under the pull of gravity into a string of atoms, would spiral and spiral and spiral. And that spiral, if laid out straight, would stretch 70 some odd light years in length. Now, mostly when we're talking about spaghettification, we're talking about theoretical things. That we know of, people haven't actually fallen into a black hole yet. Most of the time, in fact, when we do see things getting spaghettified, the dust and cluttered area around black holes obscures the flares and flashes of light that can be associated with an object being torn apart. But most of the time is not all of the time. And in an amazing case of luck and pre-planning, an international team of astronomers has been able to observe the slow demise of a star being tidally disrupted as it fell into a supermassive black hole. Last September, a variety of all-sky surveys alerted astronomers to an increase in brightness in the center of the barred spiral galaxy 2MASX J044637990-10133349. Viewed from straight above the system, astronomers were able to catch an unimpeded view of what is believed to be a star being shredded. Once the initial uptick in light was spotted, many of the world's largest telescopes pointed at the system to see what was going on. The rise in brightness didn't match a supernova, and it was located in the center of a galaxy rather than in the more traditional star-forming regions or outer areas where various novae events tend to happen. In fact, the center of a galaxy is the perfect place for something to get spaghettified. According to lead author of a new paper in the monthly notices of the Royal Astronomical Society, the idea of a black hole sucking in a nearby star sounds like science fiction, but this is exactly what happens in a tidal disruption event. According to the press release, to get a detailed look at just what happens when a star is devoured by a monstrous black hole, researchers pointed the European Southern Observatory's Very Large Telescope and New Technology Telescope at a new flash of light that occurred close to a supermassive black hole. Follow-up observations occurred over a 6-month period at multiple telescopes around the world, including the Center for Astrophysics and Harvard-Smithsonian's Multi-Mirrored Telescope, which is located at the Fred Lawrence Whipple Observatory in Amado, Arizona. This is the closest spaghettified star so far detected, and early detection by all-sky surveys allowed it to be studied before the star's material could coalesce into dust and debris and obscure our view of the system. Co-author Kate Alexander explains, because we caught it early, we could actually see the curtain of dust and debris being drawn up as the black hole launched a powerful outflow of material with velocities up to 10,000 kilometers per second. This is a unique peek behind the curtain that provided the first opportunity to pinpoint the origin of the obscuring material and follow in real time how it engulfs the black hole. The observations themselves weren't entirely satisfying. The system got brighter and fainter, and the coolest science will come later when detailed models explain the star's final days. This is our reminder that observers catch only hints of what is happening, and it is through computer models that match those observations that we tease out the details. These observations from prior to the March 2020 COVID shutdown also remind us how important it is to have regular access to the sky through a myriad of different telescopes. For the past many months, our observing abilities have been limited with the closure of numerous observatories in Chile and Arizona. Construction was also stopped at the Vera Rubin Observatory, the home of the Large Synoptic Survey Telescope. Due to the limited impact of COVID on the Big Island of Hawaii, however, Mauna Kea Observatory has stayed open for limited science and has been a proving ground for safety protocols and implementation of protective measures. Now the lessons learned at Mauna Kea are being implemented elsewhere. Construction of the Large Synoptic Survey Telescope has resumed, and Kit Peak is doing the maintenance and preparatory activities needed to reopen the facility by mid-November. Cerro Tololo resumed activities October 11th, with the 4-meter Blanco telescope and other facilities at Cerro Tololo should be resuming activities in early November. SOAR has been doing engineering tests, and Gemini South is doing maintenance with the intention to resume science later in October. While we're still seeing a steady stream of research results, the stream isn't what it used to be, and we can expect it to continue to slowly dwindle as the research is impacted more and more by lack of telescope access, lab access, and the overall difficulty of getting work done with normal efficiency in these inexplicable times. Science goes slowly, with 6 months to 2 years often passing between observations being taken and journal articles being accepted and published. This means that the impact of COVID on science is a lagging indicator. While predictions are that COVID will continue to impact the U.S. through at least fall 2021, we can expect to see the worst of the science impact still in our future, and that science impact will continue through 2023 or beyond. And no, I have no idea how the launch of the James Webb Space Telescope will continue to evolve. If I were a betting person, I'd say 2022 at the earliest and more likely 2024. Here's to hoping I'm wrong. Luckily, we have missions out there that are continuing to get us more data and are keeping us more than a little bit busy. Here at CosmoQuest, home of the daily space, our citizen scientists were part of mapping the asteroid Bennu to find a suitable site for the mission to grab a rock sample to bring to Earth. We are now 1 week away from the sampling event. We will be simulcasting any NASA live streams that are out there on CosmoQuest X on twitch.tv. According to a suite of journal articles that came out last week, Bennu is considered to be a rubble pile asteroid with material from multiple objects, including a few pieces knocked off Vesta that are all gravitationally held together. According to project scientist Vicki Hamilton, our recent studies show that organics and minerals associated with the presence of water are scattered broadly around Bennu's surface. So any sample returned to Earth should contain these compounds and materials. We will compare the sample's relative abundances of organics, carbonates, silicates, and other minerals to those in meteorites to help determine the scenarios that best explain Bennu's surface composition. Put another way, they're hoping that the few grams of material they're able to pick up will allow us to work backwards to figure out the mineral recipe that makes up Bennu. It appears to be a mixture of rocks that formed in both dry and wet environments, but the ratios and details still need reverse engineered. And next week, the needed material will get picked up out of Nightingale Crater to be flown home next year. This mission is following in the path of Hayabusa 2, which collected samples from Ryugu that will be returned to Earth on December 6th of this year. When that happens, we'll bring you the science. But until then, this has been today's Daily Space.